As a separate matter, we also talked about the improvement for sequential scan that comes from prefetching. So with prefetching, we're going to ask the disk space manager for a run of sequential pages. We're going to read ahead. So for example, on a request for page 1, we'll also request pages 2 through 5, even though we weren't explicitly asked for them. Why does this help? Well, it amortizes random I/O overhead. If pages 1 through 5 are contiguous on disk, when we do that seek to get page 1, we might as well read pages 2 through 5, and we have to put them somewhere, so we put them in the buffer pool. And this also allows computation to happen while the I/O is continuing in the background. So if that scan of pages 2 through 5 is taking time on the disk, the CPU can be doing something with page 1 that's in the buffer pool. And a way to think about this is that the disk drive and the CPU are two parallel devices working at the same time. Having seen LRU clock and MRU, what we seem to need is some kind of hybrid, because LRU does well for these random hot-cold or popular-unpopular access patterns. And when might you see that behavior? Actually, all the time. Anytime you have individual access to things, some tend to be popular and some don't. Common example, web pages. There are very few very popular web pages and lots of unpopular web pages. The same is true for blocks in a disk. Very typically, there are blocks that have popular data on them and blocks that have unpopular data. So this kind of LRU behavior for random access is quite common for single lookups. But MRU wins for repeated sequential scans of the sort we see in certain join algorithms or in repeated access to a file when you have to do iterative scans over the file. And so we want to have something that's a hybrid of both that does well. And this was noted in the early days of database systems, and there's been various ways of coming up with hybrids in the literature. There are two general approaches that people take to kind of getting the best of both worlds of LRU and MRU. One is to have the database system give hints to the buffer manager. And for big queries, where we can predict the I/O pattern of the whole query, because we have a plan for this big query, there'll be a handful of query processing algorithms in that query, and we're going to learn about them shortly, and they have very specific access patterns. So we can actually tell the buffer manager what's going to happen soon and give it a hint about whether we'll see, say, repeated scans or whether we'll see individual random I/Os. Okay, so the buffer manager, based on the query, could choose a different strategy. For simple lookups that are not complex queries, we may not have a long plan, but lots of simple lookups tend to be the kind of tasks that LRU does well. There are also policies that themselves try to achieve the best of LRU and MRU without any information about the workload. Some of them that you could find in the literature are called 2Q or LRU2, or there's a recent one called ARC. You can read about these on Wikipedia. I'll warn you that the Wikipedia page tends to frame these things in terms of operating systems and file systems and doesn't pay attention to the kinds of workloads we see in databases. So if you really want to learn about these things, you should go read the papers, many of which actually come from the database literature. As I said, it's quite common to use hybrid schemes in modern databases. For example, some systems have a special policy for index files that's different from heap files. So they'll use, say, LRU2 for their heap files, and they'll use something special for disk index files. For what it's worth, Postgres simply uses clock. You can imagine, though, that in the cloud, things are quite interesting. So a system like Amazon's Aurora, which is a hosted database that has thousands or tens of thousands of different clients and databases coexisting in the same system. It's got very interesting access patterns, and you can imagine it might be tricky to come up with a specific policy there. So you have to do something that'll work across all your users and all their databases. I mentioned that the Wikipedia page talks about page replacement in terms of operating systems, and we want to think about it in terms of a database system. And that might make you ask the question, well, if the operating system already supports some kind of file cache, why is the database system implementing that as well? Can't we simply use the operating system, or really the file system's buffers, and let it do the job for us? Well, there's a bunch of issues that come up. First, portability. Many operating systems support more than one file system implementation. And of course, many databases run on more than one operating system. So if you have a database system and you want it to perform predictably across operating systems and across file systems within an operating system, then you want the database system to control the buffer pool policy. Okay, so that's one reason, portability, to get predictable performance for the database. Now, another key limitation is that most file systems and the operating systems underneath them have limitations that can affect the correctness of a database. For recovery purposes, database systems often need to force particular pages down to the disk. They have to make sure that that page's information from the buffer pool actually makes it onto the magnetic disk device. And the operating systems either don't have APIs for this, or sometimes they have an API, but it's only advisory. So the database system can say, please flush this page. The operating system will say, I'll get on that, but the operating system actually hasn't done it. And so the database system never knows if the page has been flushed or not. And that can cause catastrophic failures if the database system doesn't get that right. And so it wants to keep track exactly of which pages were flushed to disk. Finally, as a performance matter, the database system has more information than it can give the operating system or the file system to predict page behavior. So the database system knows its query plans, and it also knows the data structures on the pages that it's working with, and it can use those to do intelligent prefetching and to do intelligent page replacement. Example, consider a scan of the leaf level of a bee tree for range search, like we saw in a previous lecture. The database system knows that there's a linked list at the bottom of that bee tree that connects the pages one to the next, and it can predict which page it's going to fetch next as the next pointer on the current page in the leaf level. But the operating system only knows about physically contiguous pages, page 1, page 2, page 3 of a file. It doesn't know about these pointers, and so it can't do the prefetching for us. The database system needs to control the prefetching with the information it knows about the data structures on the disk. There's similar issues with page replacement as we saw before. Sometimes we might want to use MRU, sometimes LRU, sometimes a hybrid, and so the database system might want its own policy based on the queries that it sees going by. And again, the operating system doesn't have access to that information. So for a bunch of these reasons, database systems implement their own buffer pools. They bypass the operating system file cache. They tell the operating system, don't cache these blocks, we'll take care of it. So there's only one copy of the blocks in memory, and it's being managed by the database system.